Hello everyone, this is Athota Rathan Babu, working as an assistant professor in the Department of Aeronautical Engineering, and I'm dealing with the course Computational Aerodynamics. And here I'm dealing with the topic, so comparison of numerical results with the experimental results. So basically here we will see how we will validate our numerical results with the experimental data. So basically, how do we validate our results, and how can we justify our results, and how can we believe our numerical results is very important. So let's say we are performing some sort of simulation using some computer techniques. So how do we believe that those results are correct? So how do we see that those values are realistic in nature or not? So these questions will come into picture when researchers do these things, and to validate these things we have to compare the experimental results with the numerical techniques. So we will see basically what are the key parameters that are involved, how do we compare, and how do we model the experiments, how do we set up the simulations in general, we will see in this lecture. Okay, so let us see basically a small bench standard cases. So let's see flat plate, and let's see pipe experiment, and let's see flow over airfoil. So how do we model the experiments, and how do we compare the numerical results with the experimental values? So first case, flat plate. Let's see flat plate. Okay, so I just want to simulate a flow over flat plate. So let's say you just know the plate is nothing but a 2D or a 3-dimensional one. So basically if you consider it is a 3D, so you will have thickness of the plate, and you will have length, you have breadth, so everything will be high. So when you want to simulate the flow over flat plate, so we can do in two ways, so numerical and experimental. So other one like additional is analytical. So where we need to see the formulation, what people have invented, empirical correlations, we will substitute those things and we'll get. Here we are discussing about only numerical and the experimental. So when we want to simulate those setup in numerical, so what we do is like, so we set up a domain, so which we know these things, so which we have already discussed. So we will set up a domain, so where we call this as plate. Okay, and we will simulate this using the boundary conditions. So what boundary conditions? So we will have velocity inlet, and here you will have pressure outlet. Okay, so this will be far field. Fine. So these boundary conditions will simulate realistically how the flow is passing over the flat plate. So let's say this is the plate, and we are considering the flow. Now the question is, so if I vary the speeds, what happens? Okay, if I vary, so the medium in the sense, if I take the flow as water, if I take the flow as air, so what happens? So will the experiments will vary, or will the simulation will vary? So what is the key parameter that is required to compare the experimental and the numerical results? So that is very important and the key factor. So there are two important non-dimensional parameters. So Buckingham Pi theorem so has given some important conclusions that so we have Reynolds number. So we have Reynolds number, which is RE is equal to, so rho V L by mu. So basically this is one of the key parameter, so which is used as a non-dimensional parameter where we can compare the experimental and numerical results. So let's say there is a similarity theorem which is called dynamically similarity. So if we have a body, so which is of same shape or different size with same Reynolds number, so we can compare those results. So let's say what we do is like in the numerical simulation, we are simulating a flow over flat plate. So let's say this is a flat plate of 1 meter cross 1 meter dimension. Okay, and we have another flat plate, so which is of 3 meter cross 3 meter. Okay, so this size, let's say this is 1 and this one is 2. So this one is the smaller one and this is the larger one. So RE1. So RE1 is nothing but the Reynolds number of the first geometry, and RE2. So this is the Reynolds number of the second geometry. So the first geometry and the second geometry. So here what we have, the shape is same. So shape is what? It's a square. So square flat plate, we have 1 and 2. So when the Reynolds number is same for the both the geometries, then the results of CL, CD and CM and CP, so all the things can be related. So whatever, irrespective of size, okay, so we can compare the results when we have same Reynolds number. So that is the key factor which scientists have found. So with these factors, people have compared the numerical results with the experimental data. So the dimensions of the numerical results, numerical bodies, or let's say experimental bodies, so may be different. So why? Because experimental things are different with respect to different cases. So people use, let's say, for aerodynamics, wind tunnel. So it might be low speed wind tunnel, it might be high speed wind tunnel, or it might be a wind tunnel which is of a large size. So based on their requirements, they will model. So let's say if you have low speed wind tunnel which is of incompressible flow, it has a very small test section. For the small test section, we will use small models. So in the numerical simulation, we can go for the actual or the large models. So we can compare those results of the experimental and the numerical when we equate the Reynolds number. Okay, so let's take the cylinder. So let's say, let us do it in the numerical way. So first, numerical. So I have created a domain. So I placed a circular cylinder here. Okay, so I am sending a flow. So with respect to RE, which is of Reynolds number. So Reynolds number here, I am taking it as let's say 3000. Okay, so this 3000. So this is what numerical. So second, experimental. So experimental, what do we have? So let us see the wind tunnel. So here first you will have the inlet. So in the settling chamber. So then you have the conversion section. So from here you have test section. From the test section you have the diffuser. So this is outlet. So in the test section you will place the model, so which is of circular cylinder. Okay. So here you will send the same flow with the Reynolds number RE is equal to 3000. Okay. So here the size. So let's say the size of this model. So the diameter, let us take it as 4 meters. So okay, here the diameter, let us take this as 1 meter. Okay, diameter of the cylinder. Now, if the Reynolds number in the numerical result and if the experimental result they are same, then the value of coefficient of pressure. So basically we mainly see the pressure distribution CP. Next we will see CL, coefficient of lift. Next we will see CD, coefficient of drag. So these values will be same. So basically Buckingham-Pi theorem has stated that if the geometries has same shape and the dimensions are different, and if the flow has the same Reynolds number, then the values of CP, CL, CD, and additionally you will have movement, coefficient of pitching moment, which is CM. So the values, the force coefficients and the moment coefficient values will be the same. Okay, so that is the conclusion which we got from the Buckingham Pi theorem. So here, using that Buckingham Pi theorem, so people are able to compare the numerical simulation and the experimental results. One very important and the key thing is, here you should have the Reynolds number same. Why? Because since we are dealing with the incompressible flow, the Reynolds number is the key parameter to compare. So when we are comparing the results of numerical and experimental for a cylinder, what we have to see is that the Reynolds number should be matched with the numerical results and with the experimental results. So that is a key factor. So when you are having the same Reynolds number, you can compare the results. So let's say you will get the CL value as let's say 0.12. Okay, so CD value as 0.05, let's say. So this is for the numerical. So and the experimental value CL will be, let's say, 0.128, let's say, and the CD value is 0.0498 or something like that. So here it will not match exactly. Why? Because so in the numerical thing, so you will have a computer aided simulated flow. So where you will actually simulate the turbulence level and the intensity of the diffusivity and the emissivity based on the key parameters which simulation controls. So where you have turbulent kinetic energy K and epsilon and omega. So these values, let's say you have the turbulent models K, epsilon and omega. Okay, so if you use RAMs, so these are the parameters. So K epsilon, K omega, so RNA. So there are these parameters which will actually simulate the turbulence and the intensity of turbulence using the numerical techniques. Now, here in experimental cases, what happens? So in the experimental cases, so the turbulence level, basically they are simulated based on the intensity of turbulence that are cancelled at the inlet. So here you will have the honeycomb mesh. So inlet you will have mesh. So the mesh will cancel out the turbulence. So basically depends on the size of the mesh what we have, depends on the stratification what we do at the inlet of the test section, or sorry, at the inlet of the wind tunnel. So the turbulent intensity will vary. So it may be 5%, it may be 10%. So these things, so there are the errors which are associated with the numerical and there are errors which are associated with the experimental. So never ever, so both experimental values and numerical values will not exactly match. Why? Because so you will have the experimental errors and you will match in the sense it will not be exactly equal to, let's say, 0.12 and 0.12. So there will be uncertainty. Why? Because you have errors associated with the numerical models and we have errors associated with the experimental models. So we need to actually see that these errors are first minimized. So first, in the numerical errors we have discussed in the previous sessions. So we have due to truncation and you have errors due to dissipative and dispersive. So we will discuss those things in detail. So about the numerical errors which are dissipative and dispersive errors, and then in the experimental errors, so first thing is so the calibration. So whether the manometers, so you have YouTube manometer, you have digital meters, so whether whatever the readings it is giving, it is accurately measuring it or not. So the instruments which are measuring the pressure for on the model, so whether they are giving the accurate results or not is important. So how much accurate it is. So what is the value of plus or minus levels of height, and what are the values that we use for the reference pressure and the reference density are particularly suited on the day or not. So let's say we take reference pressure as 1 atmosphere. So when you're conducting experiment on the day, so exactly is it 1 atmosphere or 0.98 atmosphere or 1.1 atmosphere. So those values also we need to check actually. So whatever the instrument values what we get from the wind tunnel, so it is giving exactly or not, that has to be evaluated. So we have errors associated with the experimental setup, we have errors associated with the numerical setup. So the errors coming from experimental and errors coming from the numerical, so these will result a final error actually. So that's why when you compare the numerical simulation results with the experimental, they should not match. If it is matching, so it's luck kind of thing, but it will not match in general. So you have some band, so which is let's say 5%, 2%, less than 1%. So let's say we consider experimental results as standard. So when you compare with the experimental results, so the error between the, so let's say what we do, like error is nothing but, so results of experimental minus results of numerical divided by the result of experimental, we see actually. So here how do we do it actually? So here it will be 0.128 minus 0.12 divided by 0.128. So percentage will be into 100 into 100. So this will give you what is the error with respect to the experimental values of CL with respect for the numerical values. So this is how we see the comparison between the numerical models and the experimental models. So the first very important thing is, so how do we compare? So the comparison is done based on the Reynolds number. So at what Reynolds number you are comparing, and what is the size and what is the shape is important. The shape of the model should be same. In the sense, the geometry what we are using is the cylinder. So the geometry cylinder should be same in the numerical and in the experimental, but the size can be different. So why? Because in the Reynolds number, so basically what is it doing is, so RE is equal to rho V L by mu. So here there might be different questions. What are those questions? So whether the density, so if I vary, so rho which is equal to air, water, let's say you have mercury. So what happens? Will the results vary or not? That is also important. Next, velocity. So if I change from 1 meter, 1, 2, 3, let's say till 10, or let's say till 100 meter per second, how the results will vary? So length or here length will be the hydraulic diameter. So or diameter of the difference. So the diameter. So if I vary 1, 2, 3, so on, let's say 100 or let's say 1000, so whatever meters. So what happens actually? So next, viscosity mu will be actually referred to the flow which we are having. So here what is happening is, so the Reynolds number is able to take care of different flow instincts. So what happens if I vary, let's say air, or if I vary to water, if I vary to mercury, how the results will vary and how these behavior vary. So these things also can be simulated. No need to perform separate experiment. Why? Because so when you are varying Reynolds number, so automatically the density varies, the velocity varies, the reference length varies, and the dynamic viscosity varies. So when we are varying the density and dynamic viscosity, obviously we are varying the type of fluid. So example I will give. So let's say the same the numerical thing. So the same setup. So what we have. So here again you have the cylinder, circular cylinder. Here I am doing it for air. So with a Reynolds number of 3000. Okay. So this is first setup. For the second setup, the experimental one. For the experimental one, So if I do with the water, so you have water tunnels also. Apart from wind tunnel, so you have water. So with again same Reynolds number 3000. So will the results vary? So results vary in the sense what happens to Cl, Cd, Cm? Will it be same or it will be different? So there will be some questions actually. So you just imagine. So you have a cylinder and air is flowing over it, and again you imagine you have water and water is passing over it. So water will have more viscosity compared to air. So you can think that the value of drag, quotient of drag, will be more for water and it will be less for air. So these things will come into picture when you have the first instinct that I'm conducting experiment in water and I'm conducting experiment in air. So the results will vary for sure, that you will think, but this is wrong. So the results will be same. So irrespective of the fluid, irrespective of the velocity, and irrespective of the length. So and when you are matching the Reynolds number, so Reynolds number is automatically is able to adjust the fluid density and fluid viscosity with the parameters rho, v, L by mu. So let's say here we have rho of air and V of air, and this will be the diameter of the cylinder divided by mu of air. And here this will be so rho of water and V of water and D divided by mu of water. So here what we are getting? Here we are getting 3000. So here we are getting same 3000. So what is happening? So internally, so the values are able to adjust by themselves to get the same Reynolds number. Now, so what we conclude here? So when you have the same amount of Reynolds number, the value of Cl, Cd, Cm will not vary whether you do with experimental water, whether you do with air. So it doesn't matter. So the results will be same. So this thing actually it's no need not to be with numerical. If you do the same experimental, if you change with air and water. So let's say if you change the numerical as water and the experimental as air. So you should not think that results will change. No. So here what we conclude is that whether you take air, whether you take water, it doesn't matter. So when the RE is same, the results for water and results for air as a fluid will be same. Okay. So the major conclusions what we see here is, so the Reynolds number, which is RE is equal to rho V L by mu, is playing a key role in comparing so different fluids and different velocities and different lengths. Okay, so it will take care of these things. So whether you do an experiment and whether you do in numerical. Now, so this RE of experiment should be equal to RE of numerical. So when the Reynolds number of experiment and when the Reynolds number of numerical, when they are same, if they are same, what happens? The value of Cl, Cd, Cm, let's say Cp. So you have these things. So these will be same for both experimental and numerical. What is one important major thing we need to see? Shape of body or geometry. same. So it should be same. So these things we should find. We should actually take care. So when the shape of the geometry is same, shape in the sense, when you take cylinder, it should be cylinder. When you take airfoil, it should be airfoil. So when you are comparing experimental result for airfoil, the same, it should be airfoil. When you take cylinder, it should be cylinder. When you take flat plate, it should be flat plate. The size can be different. So here if you take 1 meter, it can be 10, 20, 100 meters also. When you are equating Reynolds number, it doesn't matter. So when you are conducting experiment for air, you can conduct it for water also, based on the resources what you are available. But one important key thing is that you should equate the Reynolds number. So when you equate the Reynolds number, so you can compare the experimental results and you can compare the numerical results. Okay, and we can compare the values of CL, CD, CM. So what is advantage actually? Why we are doing this? So in realistic, let's say in real world application, so where do we use? So what is its advantage? So I'll give an example. So where we have the rockets, okay? So we have the aircraft. So basically you have first rockets, aircraft, satellites. So other examples. So these things are coming to other things. You have cars, you have bikes. Okay, this is for automobile, etc. So on. So coming to civil industry, you have buildings, you have dams, so on. So you can perform numerical simulation on rocket, satellite, and these things. But doing an experimental simulation over the rocket, large rocket, is difficult actually. So what people will do? So they will scale it down. Let's say rocket has a length of L, so they'll scale down it to 1000 or 10,000, and they will make the small models and they'll keep in the experimental setup and they'll perform the experiments based on the Reynolds number. So we have to equate the Reynolds number for numerical as well as the experimental. So when we perform numerical simulation, you can do it for actual models with the actual dimensions. But when we perform the numerical simulation, experimental setups, so using the actual dimensions is problem. Why? Because the rocket will have a length, let's say 400 or 500 meters. So based on its purpose, or let's say aircraft will have certain length, satellite will have certain length. So it will not fit to the test sections. So it will require large test section, large amount of space, large amount of humans like effort, and large amount of cost. So in order to minimize the cost, so we will actually scale down the model to 1 is to, let's say 10,000 or 1,000, such that we can fit that one into experiment setup, or let's say test section. So what we do, we perform same Reynolds number for both numerical and experimental, let's say rocket, aircraft, satellite, and compare the results. Similarly, car, bikes. So some people, let's say Volkswagen, Audi, let's say BMW, so they may actually initially perform the numerical simulation and they will have the toy which is of let's say length of 1 is to 100 scale. So those models they'll keep in the test section of the wind tunnel and then compare. So and they will have the test sections of length of this car and width of the car. So where they want to check the actual properties of the flow over the cars. So let's say for racing cars they will be seeing. So whether they are able to minimize the drag. So whether they are able to minimize the flow separation or not. So these things actually they can do it. And coming to buildings and dams. So we have the buildings. So large buildings like high-rise buildings like Burj Khalifa. So tallest buildings and the ventilation of the buildings. So these things actually can be performed using numerical simulation, and people can perform the experimental setup while they create a small scaled building dimensions and the setup of the colonies using some materials. They can keep those things in the test section and perform the same experiment what we do, keeping the Reynolds number RE of experiment equal to RE of numerical. so that they compare the results. They will see how the ventilation system is happening, how the aerodynamic load is happening over the building, whether the flow is uniformly distributing it or not. So these things can be answered. So therefore, concluding to the session, so we have seen that using a Reynolds number, a key parameter, a key non-dimensional parameter, we can compare the numerical results and the experiment results for all the fields of science and technology. It can be aerospace, it can be mechanical, automobile, or it can be civil, anything actually. So we have seen it for basically an incompressible flow. So we'll see in the next session. So how do we do for the compressible flow? So let's say when the flow speed increases 100 meter per second, what happens? So when the flow get compressed, so how do you compare actually? So what we do? So what numerical procedures they do, or how do we compare? So these things we will see in the next lecture. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.